Good day, folks. This presentation is really about vibrating screens. In another part of my series, I will discuss other types of screens like the linear screen, trommel screen, etc. But the basis of this is vibrating screen for this presentation, as vibrating screens are probably the screen that you're most likely to be using in most of your operations. And there are subdivisions of vibrating screens, as we'll see in the rest of this presentation. Now, the vibrating screen sizing or whatever is often dependent upon, I've got a few things here that I want to show you, is the vibrating screen manufacturer's manual, and I'll make this available to you as well. At least this manual gives you a basis on which to at least have an intelligent discussion with the vendor supplying you with screens. Now, the vibrating screens manufacturer's manuals was many years ago set up as a, all the vibrating screen manufacturers came together in the US and said, we better put a standard down for how we do design screens. And this is where this came about. But I do make this available to you, and I'll show you where to get that. Then the other one is, especially for drain and rinse screens and desliming screens, it's dependent on drainage and things like that. Now, the good old DSM manual, and if many of you don't know this manual is also, once again, in the 1950s about. This manual was developed by Stanley Carbon to develop the dense medium cyclone technology, and it's got general application in industry, in the coal industry, iron ore industry. I think even the new lithium industry is using it to some extent. So it really has wide application, and okay, it was developed in the 1950s, but it gives you a very good base to design a DMS plant. I also will make this available to you later when I discuss in other videos. But having said that, the other thing that you often also can get from your screen supplier is things like this that basically just give you an idea of the drainage rates, or rather, sorry, open area for the different screen panels. And I'll get into that, why that is important. Now, back to the presentation. And as I said to you, where can you get this stuff? Well, if you went to my landing page here for this offer, is https://offer.ndme-inc.com. You will go here, you will get various things here. You'll get the mass balance predictor for cyclones that I've already made available to you guys. There is mineral processing guidelines if to set up a plant. Just give you broad guidelines when you need to start a thing, when you don't know where to even start. Just give you that good initial guess. The Rosenrander size predictor, as I've mentioned, the vibrating screen manufacturer's manual, and I'll also be putting in there, which I'll discuss later, is the sizing a size classification vibrating screen based on the vibrating screen manufacturer's manual, and that will be in the next video. I'll discuss how that model works. Oh, and by the way, that model is based on the vibrating screen manufacturer's model, but that's why I do speak about LIM. LIM does have it within the one of its default unit models is based on that for screen sizing. So it's another way why I personally like LIM quite a lot. Anyway, having said that, let's just discuss why is accurate screening important. Well, if you think about it, if you were to treat particles that are, put it this way, let's say you've got small particles that can't be crushed by a crusher. You are using crushing capacity that could rather be taken by larger particles, and that just gives you an idea of that it increases plant capacity, a well-designed screen, and integration with the rest of your plant. The next one is product quality control. Of course, often products are sold on the a sizing spec in many parts in the metallurgical industry. Coal being one, mineral sands being another, iron ore being another. So just so having a good screen design often helps you with that. Of course, reduced energy wastage. You don't want to treat a particle that is already right size. You want to have it the right part of the circuit immediately. And then, of course, reagent consumption. The way it does it in general terms is a good sizing prevents very fine particles going to your thickener circuits and whatever, and then surface area is often related to reagent size. So needlessly breaking up particles, liberating more than needed, is a reagent consumed. If you think about it, just surface area increases. Now, let's just talk about the definition of screening. Screening is a separation of material particles on the basis of size. Now, what a vibrating screen does, if you think about it, it stratifies the material, and when it gets to the panel and it sees a hole, the right size, the decision is made whether it goes through the hole to the undersize or stays in the oversize. So that's basically how a screen really works. Now, the stratification of the bed material on the screen is often influenced by the bed depth, the rate of material travel. So that's why the screen actually vibrates, and the way it vibrates is also moves particles down the screen panel. And if you have a big stroke and a fast movement, you can actually make the particle hop along the thing and never see actually an opening area to actually be the decision made whether it classifies the particle or not. Surface moisture of particles, well, carryover of particles is often influenced by that, and we'll discuss it later. And of course, size distribution. Imagine if you have a lot of oversized material, you form a thick bed on top of a screen, and then the particles that are smaller never get a chance to go to the screen panel and see a hole that they can actually fall through. So that's basically that. Now, just to discuss screens further, all screens are really volumetric devices, and their capacity is governed by the following: the feed rate, the bulk density of material, and you can imagine if it's volume and you have a higher bulk density, your tonnage will go up. The velocity of the material flow over the screen. Remember I said it's how the screen vibrates in terms of its stroke. That means how much the screen bounces up and down, and not the amplitude, the frequency, how fast it turns. Does the movement, and then of course screen width. As a general rule, screen width is related to capacity, and the more you've got length, the more chances you have of a particle seeing at the screen panel deck and being able to go through the hole or not, and that of course gives you efficiency. Now, in general terms, you've got different devices work best for different sizes, i.e. hydrocyclones work well till about 250 micron. You can actually, there are unique cyclones like flat bottom cyclones that can go, they invade the space here. And of course, it's all really dependent on the SG of the particles. You remember that a hydrocyclone is actually a hydraulic separation device more than a pure size. You just use hydraulics to do the size separation. Then you've got ultrafine screening. They are very screening supplies. This is pretty high-tech stuff. I mean, me being a bit of a nerd about the manufacturing of these pieces of equipment, there's some high-tech and quality control often goes into these ultrafine screening and the creation of these deck panels. Probably the bulk of the work that you would be doing would be on vibrating screens, and that's the basis really of this discussion. And then grizzlies. And they are really, I mean, if you think about it, they're also protectors of, that's usually when material gets fed to a plant, it's the first device that the material sees before it enters a metallurgical processing facility, i.e., which is often followed by that is a crusher or whatever. Anyway, factors affecting screening is material to be separated, weight of material per cubic foot or cubic centimeter, whatever, the separation itself, the size analysis of the feed material, feed rate in tons per hour, wet or dry screen, anything special. Now, this is the basis of the vibrating screen manufacturer's manual, and when I do my next video on screening, and especially the tool to use the for vibrating screen prediction of performance, this is basically what the Vibrating Screen Manufacturers Association manual uses as the factors to define screening, capacity and performance. Anyway, types of screens that there are is the circular inline, the horizontal, banana, dewatering, and special design screens. But how are screens sized? As I said, scalping and sizing screens are essentially sized using the Vibrating Screen Manufacturers Association manual as a guideline. Now, what I need to mention, I think I have mentioned this, is that this manual was, many years, I don't know, about 50 years ago, was really written, and it's the basis which many manufacturers went out and they all did their own improvements. So the vibrating screens manufacturers often gives you a basis of discussion for the sizing of your screen, and that's what I'm trying to do when I give you these predictors as free tools for you to use. But please remember that you need to actually speak to OEM manufacturers, because there are fine nuances. So the whole purpose of what I'm doing is to give you a good taste of what it is and to help you in your screen selection. Then there's the desliming and drain and rinse screens based on the Dutch style Take Mines manual. Desliming is often used to take out the ultrafine material for in a DMS circuit, but desliming is also often used for other applications. Then you've got drain and rinse screens. This is often for media recovery in a dense medium separation plant. I will discuss dense medium separations in far more detail in other parts of the presentations that I'll be doing. Then there's truss screens that are really related to the Multotec drainage graphs. I'm quite sure other panel manufacturers use have also got their own drainage graphs, based on their panels that they supply to the screens. But whatever is in your part of the world, discuss it with them. Anyway, and then there's dewatering screens. It's empirical data. I'll give you a little bit of an outline of how it can be done. But once again, it's only an outline. I would suggest you still speak to your OEM manufacturer to just get the details right. Sizing screen. As I said, here's the vibrating screen manufacturer's manual, and you can see that the formula, the basis of the formula that's used. The material travel velocity is determined by especially the stroke and the hertz of the thing, and that creates a g-force on the particle to basically make it see the surface, basically force it onto the screen panel to actually make the decision whether it has to go through or go over. Screening efficiency is expressed as a percentage of fines that is recovered to the underflow. Now, this is often how screening efficiency is expressed by many suppliers and so on in industry of screens. The more academic way probably is using partition curves, and that is also the basis of separation to do prediction of your PSD, of your oversize and undersize. And then as I said, sizing screens are normally sized for 95% efficiency. Now, often, just as a note here, you can go for lower efficiency. If you go for low efficiency, you at least increase your capacity. So you need to make a decision when you're designing these things for your plant, whether you want to sacrifice screening efficiency for throughput. It depends on where the screen is in the circuit, so you need to define that. Then desliming screens and drain rinse screens, as I've mentioned, their basis is the Dutch State Mines manual. And yeah, you can see the formula that's used, where MPS is the mean particle size, rho is the density of the particle, and you've got these different factors, the K, 12, 8, and 10 for the different types of commodities. Now, often the modern screen manufacturers have upped these values because the Dutch State Mines is fairly conservative, but it gives you a good basis where to start. At least you won't have a plant failing on you. I mean, when you're designing often operations, you rather want the thing to work, even if it is more expensive. Granted, your project manager is often going to push you to make it a lot cheaper, but if you score a few bucks and the plant doesn't work, I think that the pain of a plant not working is far bigger than the few bucks you save. Anyway, I digress. For a drain rinse screen, application deck length is determined by the area required to drain the correct medium into the underpan of the dilatant into another underpan. Remember that table that I showed of Multotec earlier? That is the drainage rates that you can also get from that sheet. So a good panel manufacturer will have these sheets available for you. And then often the water requirements is 15 times the solids underflow volume for desliming application, so cubes per hour. And then 30 cubes per hour per meter for rinse screen application. So, but that you can get out of the Dutch State Mines manual, which I will make available to you guys later. Now, Just to look at the Multotec drainage graph that I've mentioned, as you can see, is as your now if you think about it, your open area is as a percentage changes for slotted and square meshed arc particles. And so the higher the drainage rates, the more the open area is. And remember that table that I showed at the beginning, which you can get from your supply. You can get for the different aperture or types of panel decks what the open area is. It's really just a measurement of the whole percentage holes on a screen deck of a screen. So that's basically where that comes from. Then the next one is a dewatering screen. Just to make it, is how this screen works. And what's quite nice about it, the application of the screen is not really sizing, but it is actually to dewater. Now, it's a cheap device to dewater. Often dewatering, if you were to use devices like filter presses and centrifuges, they are very expensive for the tonnage treatment in terms of capital and also operating costs because of the high centrifugal forces and filter cloths, etc. So a dewatering screen is a very nice application if you can get away with it to dewater. And slurry is fed to the back window to achieve a rapid drainage. So you can see it's fed like there, and then basically the idea is it forms basically a bed. So it's almost like your swimming pool filter. So it forms this bed and the water drains through. So high material bed captures the fine and drainage of moisture, and then high solids recovery. So you do get some solids going through here. Don't fool yourself. But because of the bed that forms, you actually score a heck of a lot in terms of moisture removal and not necessarily having your particles going into your dewatering screen underflow. And often what you can also do is post this screen underflow is put a desliming desliming cyclone, basically a cyclone, in there, and you can often just recycle the water fraction or the solids fraction back in here, and you really do know you have got a fairly watery fraction post the cyclone. Dewatering screen width is calculated to give bed depth of 80 to 100 millimeters to form a cake of dewatering. That deck, as I showed in that drawing, is inclined to reduce the travel velocity. So you're forcing a bed to be created, and depending on the speed of the motor that you're using, these are the typical rates that you can expect. Once again, speak to your screen manufacturer, OEM, to just guide you, but at least I'm just giving this to you to give you an idea of, to start an intelligent conversation. Then installation. Well, the other thing that's interesting about a vibrating screen, especially in design and installation, is the screen vibrates. And if you put it at the top of the building, you can imagine it shakes the building. It could create what you can see this picture here, especially if you get to the harmonic frequency. So that is a specialized field, so that is something else that you need to look out for when you design a screen, and that's why often it's a good idea to put screens towards the lower floors of a building to prevent this excessive vibration of the building. It has an impact on the structure that you need and then can push the costs up. So as a general rule, try and put the screens lower down in the building if you can. So that's that. Operation. The feed distribution, often that is quite something that's quite important. If you were to imagine that your feed distribution were uneven across the screen panel, you've got all the material flowing on the one side and then all the panel open areas available on the other side of the screen. So it's something small that you can do on your plants, but could have quite a big impact, and for a minimal cost to improve your plant is actually a good idea. Now, the types of problems you can get is blinding of screens, and that is what this picture here shows. If you can see it over there, it's a bit of like a clayey, sandy mush that gets formed on top of the screens. And often it is dry screening in wet season, so you can think it's a little bit like clayey, so it forms over the thing, and then often a low G operation. So that's really to do with the stroke and the frequency of your screens. Now, speak against to your OEM to guide you in terms of getting the right Gs if that is a problem. Then the another way to solve that is, of course, just to spray some water on the thing, to do spray water. You can also change the type of panel to, if it is a rigid panel, to more like a PU or a rubber panel that gives a bit of flex. Is often also a type of a solution that you can employ over here. Pegging is often when you get near-sized particles actually getting into and stuck in the hole, and that reduces open area of the screen. Now, there are a couple of solutions. Panel deck profile is an issue, so once again, speak to a PU panel supplier to help you solve that problem if it is a problem on your plant, but at least that now you know what you can do. Is one of the things. And then of course the other one that you can do is speak to your OEM about changing the stroke of the screen and the velocity that you get, the G-forces on the screen. Now in operation you also get fines carry over, and that's basically where fine material gets stuck in the oversized material and hasn't got a transfer stratify through to the screen panel, and you've got fines actually carrying over into your oversize. And it's also exacerbated often by blinding and pegging, and you can do the solutions that we were discussed previously. Now, oversize and undersize, well, that is often holes in screen, and it's not unusual on a plant, I must tell you. I've seen this happen quite a bit. Flexing of soft panels, if the panels flex, they can maybe create sort of distortions in the holes, and the particles can fall through. So that's just something else for you to consider. Now, maintenance is, of a screen. This is an endless job for a process plant manager. Is routinely clean spillage around isolators beneath screen components. Inspect isolators daily and replace deformed, and that's basically, the isolator is what isolates the screen. It's usually a rubber mounting or spring from the building. Now, if these things give way, it can shake either your building or your screen apart quite quickly. So inspecting it regularly is a very good idea. So that's probably something advice I can give you is, if you're managing a plant, walk your plant daily and make sure that those things are in good condition. Screens do fail, and look out for cracks, and that's basically what I'm warning you about. Is because the screen is a shaking device, please check out for cracks, isolators that are giving way, because a infinite life, as you can see, is 10,000 stress cycles. Now, if you think about it, how often that machine shakes per second, you can just imagine that you would use the infinite life within about a week. So yeah, regularly inspect motor couplings and exciter cardigan shafts for wear, ensure correct and vibrator motor settings, and then oil changes of your motors. So as I've mentioned in other presentations, I'll discuss linear screens, vibrating screens, trommel screens, and sieve bends. A trommel screen is really just typically at the end of a scrubber or a mill. It can be put at the particles, and because the mill turns, the particles roll over the screen deck and can be classified. A sieve bend, we'll discuss it more with when I do the DSM manual, more detail. The sieve bend is a lovely device to be able to screen finer than the aperture of the screen, the sieve bend itself. And and then vibrating mesh is often used probably in the more high-tech industry, where you want to screen very, very finely.